Imagine you come across a short movie script describing a conversation between someone and their AI assistant. The script shows what the person asked, but the assistant's reply is missing. Now imagine you have a magical machine that can predict the most likely next word for any piece of text. You could complete the conversation by feeding the script into the machine, taking its predicted word, editing it to the script, and repeating the process over and over. When you chat with an AI, that's essentially what's happening. A large language model like LLM is a sophisticated mathematical system that predicts what words is most likely to come next in the sequence of text. Instead of choosing a one word with certainty, it assigns a probability to every possible next word. To build a chatbot, developers provide text that representative represent a conversation between a user and an AI assistant. They append the user's last message, then let the model repeatedly predict what assistant would most likely say next. Those predictions become the response you see instantly. The output usually sounds more natural if the model occasionally picks least likely words at random. So even though the model itself is deterministic, the same prompt can often produce a different answer each time. LMM learned these predictions by processing an anonymous amount of text, much of it collected from the internet. To put that into perspective, if someone tried to read all the training data used for GPT-3 without without ever stopping, it would take more than 2006 years. Today's larger models are trained on much more. You can kind of think of training as a gradual adjusting the controls on an incredibly complex machine. A model's behavior is extremely determined by billions of numerical values called, what's that? Parameters. Yes, parameters or weights. Changing those parameters change the probabilities it's assigned to the next word. The word large is in large language model refers to the fact that modern models can contain hundreds of billions of these parameters. No human manually set that. They start completely random, meaning the model initially produce, what can I say, gibberish, and are gradually refined using anonymous collections of training examples. Each training example might contain only a few words or thousands. The model receives all but the final word, predicts what should come next, then compares its prediction with an actual answer, an algorithm called what's the word? Backpropagation adjusts the parameters, making the correct predictions slightly more likely next time. After repeating this process across trillions of examples, the model becomes better not only at predicting familiar text, but also at generating reasonable response for texts it has never seen before. The amount of computation involved is almost impossible to imagine. Even if you could perform 1 billion calculations every second, training today's largest language models will still take well over 100 billion years. But that's only the first stage. The progress is called pre-training. Simply predicting internet text is very different from becoming like no, no, from becoming a helpful AI assistant. That's why chatbots like ChatGPT go through another stage called reinforcement, learning with human feedback. Human reviewers identified like response that are unhelpful or problematic, yes, problematic. And their feedback further adjusts the model so it produces answers people actually prefer. Training at this scale is only possible because of like specialized computer chips called the famous one GPU, which can perform a massive number of calculations in parallel. Earlier language models processed text one word at one time, but in 2017, Google researchers introduced a new architecture called the transformer. Instead of reading one word after another, transformers processed the entire sequence in parallel. The first step is converting every word into a large list of numbers because training algorithms operate on numbers rather than language itself. These numerical representations capture different aspects of each word's meaning. What makes transformers unique is an operation called attention. Attention allows all these word representations to exchange information based on the surrounding context. For example, the word bank can be understood as the side of a river instead of a financial institution, depending on the words around it. Transformers also include feed-forward neural networks, which allow them to store even more patterns and run during training. As the data repeatedly flows through these operations, each word representation gathers richer contextual information. Finally, the representation at the end of the sequence is used to predict the next word. Once again, the output isn't a single answer, but a probability distribution over every possible next word. Although researchers designed the transformer architecture, it actually behavior emerges, from how hundreds of billions of parameters were adjusted during training. That's why it is still extremely difficult to explain exactly why the model makes particular prediction. What we do know is these predictions produce the remarkable float, surprisingly informative and often generally useful. Thank you, ChatGPT. Thank you, Jensen. Thank you, Elon Musk.